Here is Christelle's first lecture on local fields. Take it away, Christelle.
Awesome. Okay, great. All right. So I'm going to try to lecture with the mask if you can hear me, since I will be like directly spitting my droplets in your direction for 50 minutes. Okay, yeah. Hello, as Alvaro said, I'm Christelle. Um, I gave a series of talks here 4 years ago, so it's interesting to be back. It's like a different world now, and I want to acknowledge that. I don't know who or what you were 2 years ago when this pandemic started, but I know that it's been a really difficult couple of years for me. Um, I act, I mean, we'll have fun, we'll do math, it'll look like I know things. Um, but really, like deep down, I'm like really struggling mentally, and it's very difficult. I have like brain fog from the anxiety of the pandemic, and I just try to be open about it in case other people are struggling with the same things. Like, you're not alone. I think it's difficult for everyone, if it's very difficult, it's also very difficult for some other people. So, today I just want to start with an example, like a specific example that hopefully will fill up 50 minutes. Otherwise, we're going to have a shorter lecture. And my goal is for it to be fully accessible to every single person here. And I'm not saying that that's my goal for all 4 lectures, because, I mean, at some point things will get abstract. Um, but I hope that today things will stay pretty concrete and give you a kind of like, you know, I don't know what to call it, thing to look at in the distance when we're doing more abstract things. And so I'm going to start with our good friends, the rational numbers, right? So Q. Just I'll do like Hansen. That's A, B integers. Of course, we don't want B to be 0, and there's like some kind of equivalence. 2/4 is the same as 1/2. And what we want, what we want, like, you have to do what I want. So what I want um, is to value these numbers for who they are. No, so, well, for who they are to me, right? So we want to value our numbers. And the first, value that might come to your mind is the absolute value, a little presumptuous to my mind, right? Which I actually like thought about defining for you, but then I was like, what do you even say, right? I mean, like, I don't know. It's x if x is greater or equal to 0, and minus x if x is less than 0. And then I was like, oh my god, how do you find if something's positive? And then, like, anyway, right? The absolute value. That's a way to assign value to numbers. You can say, 1/2 is smaller than 10 in absolute value, right? Or you can even say things that sound wrong, like -5 is bigger than 2, if you're thinking about the absolute value. And this satisfies some property that hopefully you know about, right? The absolute value of x is greater than or equal to 0 always for all x. Um, and the absolute value of x is equal to 0 if and only if x is 0. That's the only time that'll happen. The absolute value of x times y, if I have two rational number and I multiply them together, that's the absolute value of x times the absolute value of y. And then when we do addition, perhaps we would wish that the absolute value of the sum was the sum of the absolute values. But that's not true. But at least we know that it's not bigger than that, but it could be smaller, right? The triangle inequality. So that's a perfectly fine way to value your numbers, but not the way that I want to value my numbers. So for us this week, I want a different kind of valuation. So I'm going to fix p a prime. Okay? And if you have to think of a specific one, you can think about 3. And I will define, so I'm going to call it V sub P. Later, that's going to be a value, V for valuation of some fraction AB is going to be N if P does not divide B and P to the N divides A exactly. So this is my notation for P to the N divides A, but P to the N plus 1 does not divide A, right? Like I went to the highest power of P that can divide A. And so, right, so I'm thinking, I got some fraction. I'm assuming for now that my prime, you can think of 3, doesn't divide the denominator. And so, I just look like how much does it divide the numerator? And like the more it divides the numerator, the more value I give to that number. And then I'll define it to be minus N if P does not divide A and P to the N divides B exactly. So when this situation is reversed, if P doesn't divide the top, then I look at how much P divides the denominator. I was going to say the bottom. I just call them top and bottom, to be honest. Like, I know there's fancier words for it, but and if, but I want to think of that as kind of bad, right? So if P divides the top, I'm like, yes, good, right? And then if P divides the bottom, I'm like, oh no, -5, like you take points off for that type thing. And of course, right, it can happen that P divides neither the top nor the bottom, and then I just give 0, right? It's like, well, you're not good, but you're not bad. And of course, sorry, I always forget that one. I'm going to say that it's infinite if A is equal to 0, right? If I have the fraction like actual 0, you can kind of, think of it as an extension of that, right? If A is equal to 0, then P to the N divides A for all N. So you're kind of like, just keep going forever and ever and ever. So that's going to be how I want to value my numbers. And I want to kind of see, what kind of properties this satisfies. I think I'm actually just going to start a new page. I'm always like, these aren't trees. I can have as many pages as I want. So these are the usual absolute value properties. And then I'm going to bring this here. So you can still look at it if you're not taking notes. Like that, right? That's our definition. And so, okay, well, first, right, something like that, I mean, it's just not going to be true because, the usual absolute value is like non-negative, and this one I'm definitely saying positive and negative things. Okay, whatever, right? But maybe we can think about multiplication, right? So if I have, A over B and I multiply, by C over D, and I want to take the valuation of that, right? Well, I don't know. This is just going to help me. There you go, like that, right? So if I was to take the valuation of this, I would say, okay, well, how many times, does P divide the top? How many times does P divide the bottom? And then you cancel if there's P's in common, right? If there's some on the top and bottom, right? But overall, it's going to be like, either like a positive number for how many are left at the top or a negative for how many are left at the bottom. But the point is that all the P's on the top have to come from A or C, and all the P's on the bottom have to come from B or D, and then they'll cancel, right? So however many, this has, like, maybe contributes negative P's because it has P's on the bottom, and then plus however many the other one has, right? And they will just, this will work, this plus, because they can cancel. So if this one is like a +2, like there's 2P on top, and this one is a -3, like there's 3P on the bottom. overall, when I cancel, is going to be -1, right? The 2 on top are going to cancel with 2 of them on the bottom and just leave a -1. So we see that inside this valuation, if I multiply, I don't, multiply on the outside, I add, which is not the same, but not too bad, right? I mean, if you know about exponentiating, you're like, that's what I'm going to do. That's what we'll do in a minute. But for me, it's easier to think about it as a valuation. So that's pretty good. Now, if we look at adding, things are a little bit more complicated, damn fractions, but we can say like AD plus BC over BD, right? And so there's definitely some relationship between the valuation of, these fractions and this big one, right? So if, for example, A is like P to the N times some number K, and C is P to the M times some number L, right? Then you can see that whatever D and B are here, I'll always be able to pull out the smaller one of M and N, right? Because like I'll just be able to like factor it right out. If they're equal, right? So if M and N are equal, then that's a little weird. I could like pull it all out. And then like who knows what could happen? Like maybe this term, what's left could have like extra p's, like just by like adding, right? Like sometimes primes happen. So yeah. So let's see what happens. So if say N is strictly greater than M, right? Then this is going to get to be too much. We're going to go to another page. Oops. It's not all for now yet. That's the big reveal at the end. Just like don't tell the others who haven't had it spoiled. Okay. So if N is less than M, right, then I'm going to have, if N is greater than M, then I'm going to have that AD plus BC is P to the M, P to the N minus M, K plus L, right? So my point here is that if N is bigger than M, then definitely this thing cannot be divisible by P because of the L like left over that's not divisible by P, right? So, okay, as a convention, like I'm not being silly, right? So here the GCD of L and P is 1, and of course the GCD, right? And so this whole thing is not divisible by P, but if N is greater than M, if N is equal to M, okay, and without loss of generality, one of these two things happen. If the other one's bigger, you just, flip the fractions, right? Then you have that AD plus BC is P to the N, which is the same as P to the M, right? But then that's K plus L, and this could be divisible by P. Right? I mean, we just don't know now, because when you have two numbers that are relatively prime to P and you add them up, they might end up being divisible by P. And so anyway, what ends up happening here is that when you add two numbers, the valuation that you get is always going to be greater than or equal to the smaller one of the two. Right? So here, if one of them is strictly bigger than the others, you see the smaller one pulling out, right? So, you'll at least get that, so greater than, here M would be the minimum, with a possibility, if you have equality, that you could even like pick up more P's by kind of happenstance, right? But also with the knowledge that if they're different, then you will hit exactly the minimum, right? So so this is true, okay, but we also notice that with strict inequality, only when the two valuations are equal. Okay, if the two numbers have unequal valuation, it'll always be the smaller one because of this kind of phenomenon. And if the valuations are the same, then you could kind of like win extra powers of p, maybe. Okay, so that's my work, and I think that back. Oh, this is what I wanted to do here. I'm going to fill that in here, right? Is less than or equal to. Oops. Oh, sorry, it's greater than or equal to BP. A B. The min. All right, so we have, right, this property, which kind of translates with this one if we go from a times to a plus, and then this triangle inequality about addition, which I don't know, like just has this like weird kind of analog. And one way to get them to kind of like agree better is to go from a valuation to a different kind of absolute value. So I'm going to do that in case that's helpful. Right, so to make something more like an absolute value, take the absolute value of some fraction a over b, but I'm going to put like a little sub p, so that's going to be the p-adic absolute value to be p to the minus the valuation of a over b. And then with this definition, right, this like the valuation of xy is the valuation of x plus the valuation of y, right? That just becomes that the absolute value of xy, right, is going to be p to this valuation, and now the addition is going to break up over the exponent and is going to end up being the p-adic absolute value of x times the p-adic absolute value of y, right? The kind of like step in the middle is this one. Is this one where you can break up an addition into a multiplication, and so that multiplicativity of absolute value remains the same, and then this VP of x plus y is greater than or equal to the min of VPX VPY. Well, okay, so when you multiply by -1, you have to flip the side of your inequality. I always have to tell myself that, right? So this tells you that the p-adic absolute value of x plus y is going to be less than or equal to, right? Because of this minus sign up here, that flips the inequality if I were to multiply through by -1, however you like to think of your inequalities. And then, right, whichever one gives you the smaller of these numbers gives you the bigger one of those ones because of the negative, right? So it's going to be less than or equal to the maximum of the absolute value of x and the absolute value of y, which actually, that's certainly less than if you added them, right? So, this is even stronger than the triangle inequality. You're saying, right? It's not even like you know, the usual triangle inequalities, like, oh, it's shorter to go straight home than to stop by the store on the way, right? And this is like, I don't know, it doesn't even make sense, right? Like, it's like, you can stop by the store, it doesn't matter. Like, I don't know. I was like, I'm not prepared to push this analogy. Okay, but it's stronger than that. You can add a stop and it's not worse. And then, you know, there was this extra condition up here that I was like, oops, wrong pen tool. This one, right? That I was like, I don't know, you know, like there's not, this can be positive or negative. But now, you know, that I've taken this to be p to the whatever, then I will get that condition, right? So actually, the p-adic absolute value of p is certainly greater than or equal to 0, because a positive number to any power or a non-negative number to any power is not negative. But also, right, only the number 0 has valuation infinity. And if you think of like p to the negative infinity to be 0, then only the number 0 has absolute value 0. With I guess this goes on that side. So, for me, in my heart, I always think of the valuation, not the absolute value. So, you know, that's how I will be thinking about it. But if you want to relate to facts you know about, or when I want to relate to facts I know about the absolute value, then I have to switch to the absolute value. So I'll be doing a little bit of back and forth today between the two. But moving forward, it'll be mostly about the valuation. There's not really an analog, right, of the valuation for the usual absolute value. Like I couldn't go back to the beginning of, you know, my presentation and be like, you know, so I started with valuation and then I did the p-adic absolute value. If I started with a like normal absolute value, like I can't go back to a valuation. Like that one doesn't have a little v that goes with it. Only one of the reasons why this talk's not about the real numbers. All right. So maybe let's do a couple examples to give people a time to breathe and to think of their questions, right? So the p-adic valuation of 1/2 is 0, right? Neither the top nor the bottom is divisible by 3. So I am neutral about this number. And so the p-adic absolute value, right, is 3 to the 0, which is 1. The p-adic valuation of 1 over 18, well, the top's not divisible by 3, but the bottom's divisible by 9, so that's a -2 from me. And so the p-adic valuation is thus going to be 9, because I do take 3 to the -2. So that's kind of like a big number. And if I take, you know, 27, that's very divisible by 3. I'm very happy. I'm going to give you a 3, right? And then the p-adic absolute value is just 1 over 27. Okay, these ones happen to be the same. I try to compute like what 2 times 27 was, and then I was like, oh, I already used 2, and then I was like, what about 5? And then that was too big. So anyway, right? They don't have to be like the same number. Like here, the valuation of 1 over 18 is not 18, right? It's just like 9. So anyway, right? So we see that, you know, I mean, I think of them as like, I like them because they're divisible by 3 a lot, right? They have positive valuation. That means they're very small in my absolute value. And the numbers that I don't like, right, I'm like, boo, you're divisible by 3. I don't like that. That means they're very big in my valuation. And then the numbers that I'm neutral are like medium size, like they're all size 1. I give them all the same size. What are your questions about all this so far? Anything I can clear up before we go? Yeah. Yeah. That's like a normalization thing that makes things nice, but you could pick E if, I mean, like personally, I'm like a transcendental number in this economy, but you could do that. You could do that. Yeah. Yeah.
Definition where to make something more like an absolute value, and you said that yeah, that just to understand, where does that come from? Like, why would you do that?
Well, I mean, for me, and I can't speak to the historical reasons, right? But for me, in my heart, if I see a plus and I want a times, I'm like, I'm going to exponentiate this. You know what I mean? If I see a times and I want a plus, I'm going to take a log. That's just the way, right? And so, like, if you want, you're like, dang, it goes from times to plus, and that annoys me, then you should do that. Now, right? So that part for me, because I accept, that exponentiation is like a group homomorphism from the additive and multiplicative. You can say that fancy, right? For me, it's the minus that really gets me. Like, I'm like, why minus? Like, why not just p to the valuation? Like, wouldn't that be simpler? But then, right, you wouldn't have this inequality. Like, the inequality would be the wrong way. So each of the things are for things to work intuitively, right? For the multiplication to be a multiplication, and for the triangle inequality to work instead of being some kind of even weirder, like, opposite quality. All right, well, let's carry right on. So I've talked a lot about good and bad, right? So let's so we're still in Q, and let's take a set, right, of all of the elements in Q that are not bad. Okay, the not bad numbers. Right, so I'm allowing the ones that leave me neutral, and then I take all the good ones, but none of the bad ones. All right, if I put it in absolute value terms, these are the ones that have absolute value less than or equal to 1. Okay, so if I was talking about the real numbers, I would be talking about, the interval from -1 to 1. I don't really know what I would be telling you about that interval. I mean, like, because I didn't design that class. I'm sure I would find something, right? But here, there's something good that's going to happen to us, because if X and Y are both in that set, then, of course, X plus Y are going to be in the set, right? Because, X times Y is the one that I want to do first, right? Because the valuation of X times Y is the valuation of X plus the valuation of Y. And so if both of them are good, then certainly when I multiply them together, right, either, neither were divisible by P on top, that's fine. They won't, become divisible by P on the bottom. You know what I mean? Like, think back to X being a fraction, right? I'm saying, okay, both of them, the denominator is not divisible by P. If I multiply them together, the denominator is still not going to be divisible by P. But once that I've said it like that, right, if I have X plus Y and they're fractions, and I add them, that one is a B, right? If X and Y were both in my set S, that's saying that their denominator is not divisible by P. When I add them together, their denominator will remain not divisible by P. And so that's what's special in this situation. That doesn't happen with the usual absolute value that people have been selling you your whole life. You could have had a ring all along, and they took that from you. Right? Because in the real numbers, if you have numbers that have absolute value less than 1, you can multiply them together. Like, that's fine. They'll remain that, but you can't add them together, right? Eventually, like, they'll come out. They'll become big. This can't happen here. Kind of the numbers are trapped, right? By this ultrametric inequality. Oh, sorry. This one actually is the one I want to, right? Is like, well, if you were both not too big, you know, you can add not too big numbers. They're not going to get bigger. Like, you can't leave that. So actually, this is a ring. And that's nice. So Hansen's whole thing, right, is starting, you know, with the integers and the rationals and like taking extensions of that. So in this lecture, we're going to start almost from the same place. Like, I start with the rationals and, you know, the integers, but it's actually, I'm not going to take the integers as my integers. I'm going to take something more like this as my base ring, right? Like these like good numbers with respect to this p-adic absolute value. And we'll see that so many more things are true because this is going to be nicer. So let's actually, right, what is this set S? Or, you know, so this is actually denoted Z sub P in parentheses, right? So this is all the fractions in Q with, you know, I'll just say P does not divide B, right? The ones with no bad denominator, no P's in the denominator. And we call that, sorry, let me put myself on do not disturb. I just got a notification on my watch from my son's daycare that there's a new picture of him posted online. And I was like, okay, I don't think we all need to know about that. Like, he is super cute, don't get me wrong. But I don't know if you feel the same way about him than I do. I actually hope not. That would be weird. We don't know each other. So the integers are inside this ring, right? You know, they definitely, but there's more stuff, right? Like 1/2 is in there. Well, I guess it depends. Sorry, in my heart, piece 3, 1/2 is in that, right? So there's more things in that ring than in my original integer ring. So what are some facts about this ring, ZP? Oh, sorry, and I forgot to say, this is actually and called the localization of Z at the ideal generated by P. All right, so P is still an ideal in this new ring, right? I can still take, you know, of all these fractions where P does not divide the denominator, I can look at the fractions, you know, whose top is divisible by P versus the ones whose top is not divisible by P, right? So, you know, to be clear, this ideal is going to be AB in ZP, but now I require that P divides A, right? That like there's actually something there. And actually, every element in ZP minus P, right? Every element that's not in that ideal is a unit in that localization. Okay. So what I mean, right, is so like this 1/2, it has an inverse in here too, right? Because I'm only allowing because I am allowing denominators that are not divisible by P. That means that if your top's not divisible by P, then it can be the denominator of an element in that ring. And so this tells you that actually this ideal is now the unique ideal, the unique maximal ideal in the ring, right? Like there's that, right? And then I just like told you about, some ideal P, and I was like, everything else is units. And as soon as I put a unit in an ideal, I get the whole ring. So this has to be the unique maximal ideal. And so earlier I was talking about how things are going to be nicer, right? Is because what I've done is I've started with some ring Z that had like a bunch of prime ideals. Jesus, who can deal with that many? And now I only have one prime in this bigger ring. And that's just nice. Like having one prime is easier to handle than having many primes. And so that's where, the niceness in the theory is going to come from, is that we only have to worry about one prime. We've kind of killed all the other ones. So this is an example of something we'll call a local ring. So a ring with a unique maximal ideal. And then, if you care to know, it's still the case that if I take my ring and I mod out by that ideal, I get the finite field with p elements. So it keeps the same residue field, right? If I had done like Z mod P, I would have gotten the finite field with p elements. And now this ring's a little bigger, so you're like, oh, maybe something bad's gonna happen. But no, when you mod out by P, you still get FP, because the extra stuff in here, right, like was already gonna be a unit. So now, once you give a size to things, right, once you're able to like value things, you can start seeing holes in things, right? Because like now that you know that things are close to each other, you can be like, hey, you two are like really close to each other. Like there's something, there could be something between you, right? Or like you should be getting closer to something. And so in my last, I don't know how many minutes, I think I started like a couple minutes late, but I'm gonna try not to go much further. I'm gonna talk a little bit about the completion, right? Completing this ring. So, so let's go back to the usual absolute value, just to connect to what you might know, right? On Q, right? You notice that there are sequences that are Cauchy but don't converge. Right? And so a Cauchy sequence is that for all epsilon greater than 0, there exists n such that if m and n are greater than equal to n, then xm minus xn is less than epsilon, right? So what I'm saying is, I have a sequence, I have a whole bunch of numbers, right? And like at some point, they all get like really close together. Like past a certain point, they're all in this like one tiny little ball, right? And the further you go, the tinier you can get that ball to be, right? You can get epsilon to be smaller and smaller. So you kind of imagine that like in the end, the ball is gonna be so small that it's gonna be a point, and that point is gonna be the limit of that sequence, right? They're just gonna get closer and closer and closer. But the problem, right, is that it doesn't converge, like not in a kind of like diverging way, but in a like it goes somewhere and there's nothing there, right? There's a hole. So that's what I meant. Like when you have a size, you have a notion of being close, so then you can be like, dang, like it looks like it should be close to something. It's like when you're on Google Map and like you look up, there's no building, you're like, there should be a building there, right? Like I went somewhere. So that's like what I meant. It brings your attention to kind of like what's missing. Like you're like, oh, these things are close together, like there should be something there. Okay. This happens also with the p-adic absolute value. And so let's take p is equal to 3 again, right? The only prime. No. And you can have, a1 is 1, a2 is say 1 plus 3, A3 is 1 plus 3 plus 9. A4 is 1 plus 3 plus 9 plus 27. Okay, you see the pattern? I always add one more power of 3. I was going to say, and then the next one would be, and I was like, I don't know the next power of 3, but I actually do. It's 81. So the next one would be 1 plus 3 plus 9 plus 27 plus 81. Right? In the usual absolute value, this just like diverges to infinity. These numbers get bigger and bigger and bigger. But when I think in terms of my p-adic absolute value, right? Actually, these numbers that I'm adding at the end, they get better and better and better, and so they get smaller and smaller and smaller, and I'm adding something small, like it feels like it should convert, right? Like they're going somewhere, there should be something there, but there isn't, because there's no integer like that in the integers, right? So I always am very optimistic about how much I can fit on like the little inch at the bottom, like it's like the Mary Poppins inch where you like put more material, like her bag, right? And so in this case, right, imagine that you take, an minus am and say n is greater or equal to m, right? So this one would be, 1 plus 3 plus blah, 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 like up to plus 3 to the n minus 1. And this one would be like 1 plus 3, blah, blah, up to 3 plus to the m minus 1. So this would just be 3 to the m plus 3 to the m plus 1. And that's 3 to the minus m. Right? So if this one has more powers of 3, this one takes out kind of the early ones. So I'm only left with the tail of powers of 3. And I'm like, oh, how divisible by 3 is this? Very, right? It's divisible by 3 to the m. So its valuation is going to be 3 to the minus m. Oh, sorry, the absolute value. The valuation would be m, and then the absolute value would be 3 to the minus m. See, that's why I have to do valuation, not absolute value. But, right? So as, m gets big, this gets small. So this is the Cauchy sequence, but it doesn't converge, right? Not in Q. So we do what mathematicians do, and we just make it converge. We put something there, right? We just, okay, so we add in all of the limits of all the Cauchy sequences to get the completion. All right, and so I'm gonna take just a couple minutes. So this completion is called, this is called the p-adic integers.
Why would this convert to 0? Why does this convert?
Well, I mean, like if you just think like normally, like, of the numbers that are in Z or Q, I mean, there's no limit to that. Like there's no like one number Z like that. So I mean, it's kind of hard, to like completely analogize with the rationals, right? But like imagine the decimal expansion for root 2, right? It's like if you only use decimal expansions for the rationals, Like you can never get that one, right? Like there's no decimal expansion for a rational that's the decimal expansion for root 2. So like there's something there like that keeps going forever. But yeah, so here, right, there's going to be something there that keeps going forever. It's not going to be 0. It's going to be the difference, right? So I'm not saying that this approach is 0. I'm saying that these numbers get close together. So there should be a number there that they're going to. Maybe I'm about to say, maybe that'll help. So this is called the p-adic integers denoted ZP. Okay, no parentheses. And the Z with the parentheses is now gone forever. Like I'm unlikely to use it again. Okay, so this one is Z without parentheses, and that's the p-adic integers. Yep.
What object we just to get?
Z for now. Or Z round brackets P for now. Yeah. So, well, I was leaving it vague because if we complete Q, we get what we call QP. So, I mean, you can complete one or the other, and you get one thing inside the other one. So the set ZP, every element in ZP, can be written as a power series in P. And but it's allowed to go on forever, just like a decimal expansion is allowed to go on forever. Like we accept that you can add, 1 over 100 and then 1 over 1,000 and then 2 over 1,000,000 and then and you add more and more. You're like, oh my god, you keep adding, stop doing that. But no, it converges. Like it's fine to get small, right? So you have to think like these get small, so it's fine. You can just keep putting more of them and that'll still be a number. So like that's the limit that it goes to, right? Like this limit here, I just make up a number that's 1 plus 3 plus 9 plus 27 plus 81 and so on. Like that just keeps going. And I'm like, that's a number now. That's a valid thing for me to think about. And so that's the limit. I just make it be there. And so the AIs can be chosen to be between 0 and p minus 1. And that's contained inside QP, which that one allows sorry, I'm doing summation notation for that. Okay, AI P to the I. All right, and I will say one last thing that Keith is going to need in his presentation is that, so the way, right, I thought about them as kind of like sequences, like infinite sequences that I just like declare to be convergent and be legit, right? Like, I mean, I could have always written like A is the sum of 3 to the I is equal to 0 to infinity, and just been like, accept this symbol in your life, right? And it's like, I can do that. I can just write that. It makes no sense, but whatever, right? But now I like made sense. So that's what I mean. In my heart, I just think of them as sequence, like series that used to be formal, right? That used to just be an idea in my heart. And now they've become like actual numbers that I'm allowed to play with, right? But another way to think about it is to think of ZP as what we call like this inverse limit of Z mod P to the, well, I guess in my notation it would be P to the I, right? Where you think of this element, which I think of as like one series, you can think of as a system of numbers right? Like the partial sums, and then this one is in Z mod P, and then this one is in Z mod P squared, and then this one is in Z mod P cubed, and so on, right? So I'm kind of like taking it step by step, like, oh, here's just the first term, it's in ZP. The first partial sum, it's in ZP squared. the third partial sum is p cubed and so on, right? But not just like willy-nilly. I'm not allowed to just take like an element in z mod p, an element in z mod p squared, an element in z mod p cubed. I need them to be compatible with each other, right? So it's like, you know, when I write a number at this step, it's kind of beginning is the numbers before. So you can call that like a compatible system of elements. Or I'm not sure exactly how Keith's going to call it, so I'm not going to try to guess, right? But that's another way to think about these p-adic integers. So I'm going to stop here. Sometime today, I'm going to post some homework. So there's another example like this that's pretty simple that I think you can think through to get used to these like ultrametric inequalities and all that with a polynomial ring. It's totally normal. And just like asking you to think about that. And then tomorrow I'm going to start with like the theory, right? We'll be like, okay, here's a local ring, a discrete valuation ring, you know, the theory of it. But hopefully you'll have this like p-adic integers and those polynomials over a finite field example that I'm going to put out. I'm going to put them out on the Zulip, I think. Is that good? Yeah. So I'm going to put them like I made like there's a place in the Zulip. You know what I'm talking. And if not, I'll be here tonight, right? There's problem session. Yeah. So I'll come back for that. Or maybe I'll be there all along. Who knows? I don't.